All right, thank you very much for joining. This is, I think, is the third and a half edition of Game On Seminars because last one was a non-interactive session that we held only on YouTube. This week we have assistant professor David Fridovich-Keil from the University of Texas at Austin. Professor Fridovich-Keil received his PhD from Berkeley on algorithms for game theoretic motion planning, and actually it was very interesting for me to study his work because his papers were some of the first papers that actually were, mixing MPC techniques, model predictive control with game theory. And I think it was a very interesting piece of work. But then later he continued with related and also a lot of also unrelated work, but like David Fridovich-Keil continues on doing research on dynamic game theory, optimal control, and interactive systems, multi-agent systems, especially traffic systems and autonomous driving problems. And recently you received an award, right? The NSF National Science Foundation Career Award. So we're very excited for this talk, and thank you very much for joining. And I let the word to you.
Okay, well, thank you so much for the kind introduction and for having me today. It's a pleasure to be with you, and I hope one day to make my way over to Stockholm in person. But for now, it'll have to be this way. Today, I wanted to tell you about a couple different lines of work going on in my group over the last year or so that all sort of center on this idea of kind of trying to understand or exploit properties of information structure in games. So it's a bit subtle, and I'll sort of walk through a lot of details, but that's kind of the general theme. As Emilio said, I actually kind of got into this line of work through exposure to problems in autonomous driving, motion planning, model predictive control, all in the context of autonomous driving and traffic. So I've kind of shown a few different little snapshots of what different applications for the work I'm going to tell you about, might be. So I've talked with people in power systems, in aircraft routing, as examples, but for the sake of today's talk, I'll give most of the examples through the lens of autonomous driving and traffic, so like the image on the left. If you're thinking about motion planning for vehicles and traffic, the typical way to think about problems like that would be through the perspective of model predictive control or receding horizon control. But it's actually not going to be so hard to see where games arise and how they fit in. So I want to just walk us through like a quick example to construct a game in these settings just to make the picture clear for everyone. So imagine that you're this black sedan trying to make a lane change. If you're at a company like Waymo or one of these other AV companies, the way you might think about this problem is you might write down some objective function that basically maps the planned sequence of controls to a cost that basically tells you how good the lane change is. And of course, there might be all kinds of constraints. Here I've just written some simple ones imposing like vehicle dynamics or making sure the sort of trajectory starts at the right initial condition. Here, X is the state, U is the control. Bold, I'm trying to denote like sequences over time, just to sort of get that out of the way, but I'll make it all clear later. Now, of course, there's really other drivers out on the road, there's other vehicles, and sort of the predicted trajectories that those other vehicles will follow features into the problem we want to solve. And here I've written down that connection through the objective function. So I've said that, hey, the way that we score how good a planned maneuver has to do with what we think others are going to do. It could also feature into constraints. For example, if I had constraints on collision avoidance, then I would have those blue X2 and X3 predicted trajectories of agents 2 and 3 appear in some sort of constraint. But either way, from here, it's not too much of a leap to think of agents 2 and 3 or any other drivers on the road as decision makers in their own right, and therefore that the predicted trajectories we're expecting them to take actually arise from decisions they're actively making. And so, if we're thinking of our own decision problem as an optimization problem, then why not think of the other agents as solving similar optimization problems. So all I've done is copy pasted the same, agent one's problem two more times, swapped out the indices carefully, and basically now we have three optimization problems, each one reflecting the decisions that the three agents are trying to make. And each agent's problem depends upon the decisions of the others. And so they're all three problems are coupled. This is exactly the idea of a game. And this is where we're going to go. Okay. I always want to pause here, just make sure there's like no uncertainty about anything I've said so far. Any questions?
Yeah, see none. And just once we're at this point, I want to extend the invitation also to the people in the chat if they want to participate, and they can write their questions there, and then we will read them whenever we have time for that.
Fantastic. Okay, so if there's no questions, let me keep going. I'll pause several other times. Okay, so with that sort of context in mind, let me just sort of start to lay down a bit more formalism. So there's several kind of key ingredients that are going to make up a game, specifically a dynamic game, one that's played over time. The first one, I think, is the objective. So what does each player want? I'm going to always denote this as like a function. I think I'm always going to call it J. There will always be a superscript to indicate which agent or player it pertains to. And the objective in general can depend upon an entire sequence of states the game traverses, sort of different states of the problem over time, and also the actions of all the players. So the states are X, the actions or controls are U. Subscripts are time, superscripts are player. Bold is this kind of aggregation. There's also rules, or dynamics to the problem. So from a controls perspective, this is super standard, obvious stuff, but basically, just to say it, we always need to specify if the game is in some state and all the players take some actions, what's the next state? I'll always be working with deterministic problems in this talk, but in general, of course, we could have all kinds of other stuff going on. And then the more interesting part to me, and the focus for much of this talk, will be information structure. So this is sort of trying to answer the question of what does each player know when they have to make a decision? What is the input to their strategy? So I'm here writing down the ith player's control decision at time t, uit, is some function gamma it of whatever information they know. And we'll need to be careful when we sort of formulate a problem to specify this information structure. There's also all kinds of different solution concepts that relate to these ideas, and particularly relate to the information structure quite often. In this talk, I'll pretty much be focused on variants of the Nash equilibrium concept, and I'll sort of write this down more carefully in a minute. But just at a high level, a Nash equilibrium is a set of strategies where if player I looks out at all the other players' strategies and kind of holds them fixed, then player I is happy with their own strategy. So that's the type of equilibrium we're going to look for. But as we'll see, there's different refinements, different types of Nash equilibrium that satisfy additional properties that we're going to care about. Okay, so with all that out of the way, the talk is broken down into four segments. In the first, I'm going to give us, it's almost a tutorial, just a quick run through of two fundamental building blocks in dynamic game theory. These are basically going to be games with linear dynamics, quadratic costs. They're the game theoretic analogs to LQR problems. And specifically, we'll look at what happens in sort of two extreme cases of information structure, and those will then kind of inform the later parts of the talk, which are then going to sort of get into some research we've done on these topics. Looks like maybe there's a question or something. No?
No, I don't think so.
Okay, all right. Zoom popped on for a minute. Anyway,
all
right,
okay.
So let's get into it. So linear quadratic games, like I said, this is a game with linear dynamics, quadratic objectives for all the players. It's the sort of first, maybe not the first problem in game theory one would see in a textbook, but it's a very early one you would see. Um, and if you're familiar with OQR, I'm sure probably most people here have studied OQR backward and forward, but it's the game theory analog of LQR. Here I've written it in discrete time over capital T time steps. So every player basically solves a quadratic problem like this. To break it down a little bit more, what I'm saying is player I is minimizing a quadratic function that depends upon all the agent's actions. So this term on the right-hand side, uh, summing over players j1 to n of some quadratic term. So that's sort of saying that player I cares about what all the other players are doing. And the bottom is just saying that the dynamics of the state x evolve linearly as a function of all the agent's actions in the prior state. Hopefully nothing too wild here. Something that I want to point out here that I think will come up again in some places in the talk, but it's also just I guess something I didn't quite understand when I first saw this material is it's a little strange maybe to think of player I caring about player J's control input directly. When I at least first encountered this, I remember being concerned, when would that ever physically happen? Why would I ever model a problem this way? Um, and the sort of answer I've kind of come up with, and I've actually seen in practice being used quite often, is that this is a way to encode politeness. So if you're thinking about driving or making a lane change like I showed before, um, it would be quite natural to encode sort of how polite is my maneuver by making, a score, making scoring the maneuver with high cost if it's forcing another player to say accelerate hard or brake very hard or steer very aggressively. So that's where maybe some of those terms on the right-hand side of the cost are showing up. I'm not sure. I can't see my mouse, so I assume you can't. But this sort of right-hand sum in the cost function, that's maybe one way to interpret where those terms are coming from. Okay, so that's the basic cost structure and dynamics, but I need to tell you about the information structures we're going to talk about. And I want to walk us through the sort of two polar opposite cases of information structure. I think the naming is a bit unfortunate, but they're the feedback structure and the open loop structure. When you're playing in feedback, you're basically saying that at every time t, I have my eyes open and I know I'm gonna sort of see what the world looks like and I'm gonna see the state when I have to make a move, when I have to choose a decision. So I'm keeping my eyes open. It's a bit unfortunate because there's a contrast to open loop decision making, open loop information structure, which is saying I have my eyes closed. I know I'm gonna have my eyes closed when I make a decision at time t. All I know is what time it is and where I started, what the state was at time one, the initial time. So open loop is like your eyes closed, feedback, closed loop, this is like your eyes open. Anyway, a bit confusing, but that's what it is. And lest anyone be sort of thinking that these are actually, subtle and not going to influence things very much. Actually, it's very easy to construct examples where these information structures yield wildly different Nash equilibria. So, so here I'm just showing an example that I always give people to illustrate this point. So think about a two-player game. Let's think of double integrator, like linear systems. Sort of everybody sort of has a position and a velocity in the plane. Control decisions are accelerations. Player one wants player two to go to the origin. Player two wants to approach player one. So think of quadratic ways to encode those objectives. And both want to exert minimal control effort. So player one is starting at the bottom right, player two is starting at the top right. I've marked where the origin is, and I'm showing you the feedback and the open loop solutions in two different colors. Take a minute and somebody brave tell me which do you think is which? So is green open loop or feedback? So just to repeat the question while folks are thinking, player one wants player two to go to the origin. Player two wants to go wants to be near player one. Neither one wants to exert much control efforts. They're both having a quadratic penalty on their own controls. And they may start with some initial velocity, and the controls are the accelerations.
We had somebody in the chat actually that maybe. So Umar is saying that the green is a feedback control low.
That's right. Yes. So green is the feedback control. So what's happening in green is it's saying that player one knows that player two is going to see it for the rest of time. And so player one also knows that player two wants to go to the origin. So in order to get but player one knows that player two wants to go to player one, and player one wants player two to end up at the origin. So put all that together, player one understands that if I drive to the origin, player two will see me and will want to be near me, so they'll go to me, and therefore they'll go to the origin because I'll be going to the origin. So I'll be happy. Player one, will be happy, and then player two can sort of flip that on its head and make the same assessment. On the other hand, open loop is in blue, and what's happening here is, if you think from player one's perspective, player one knows that player two will never see it again. So solve the initial condition, solve the initial velocity, but is never going to see anything player one does in the future. So then basically player one, realizes nothing it does will ever influence player two. So the best thing to do is just minimize control effort, because the only sort of state-related objective player one has is related to player two's states, player two's decisions. So player one does nothing, continues in a straight line in their, following their initial velocity. Now player two, sort of the best response to this open loop trajectory is for player two to kind of make a sort of approach like you see and eventually get close to player one. So, I think you can sort of reason through this and convince yourself that these are the right answers. But maybe taking a step back, something that's, I think, really clear in this example, and again, it's not hard to construct these types of examples, is that not only are these solutions yielding wildly different trajectories, but if you try to sort of do the standard MPC thing of closing the loop and receding horizon by sort of replanning very rapidly as the state evolves, it's not going to the open loop planning, even if you do it in receding horizon, is never going to give you the feedback trajectory. So I don't really care how often we try to replan. If we're always solving for open loop solutions in the game theoretic setting, player one's always going to be exerting zero control effort. They're always going to be going in that straight line. Player two is always going to be approaching them like you see, and they're never going to end up at the origin. So fundamentally, these problems are immediately exposing like a issue with the intuition we develop in MPC. Okay, so enough intuition, enough.
Sorry, David, that was yeah.
Sorry, David, break the flow with a question. Here, when you say receding horizon here, you mean in the MPC way? So
Yes.
planning or okay. And I'm a bit confused because in a sense integrates feedback, right? So
Yes.
I'm quite surprised that you can't obtain the same behavior of closed loop equilibria like that.
Yeah, I was too. But yes, you can't. So as long as you're always, at every time you solve the MPC problem, you're always looking, if you're always looking for an open loop Nash equilibrium, I mean, just we'll see the math of why this is true in a minute, but basically, player one is always going to realize, hey, the right thing to do, no matter what the state is for me to do nothing. And so, I mean, doesn't matter how fast you resolve the problem, the answer is always going to be do nothing for player one. Yeah. So now there are maybe some creative things you could think about doing to try to encode sort of a more proper sense of feedback in the information structure sense into a receding horizon MPC. But I think fundamentally what all those things are doing, it would be trying to encode the feedback information structure. And so if you wanted to do receding horizon planning and end up with the green solution here, you should do it with feedback information structure. that's essentially the point.
We have an additional question from the
Mhm.
chat. So can you please comment on what does it mean to have feedback on the state from the other agents? Is that a privacy concern, assuming that
Oh,
you
yeah.
can observe the state of the other agents? And will it make more sense that you can only observe the some outputs of other agents?
Yes, yes. So so first of all, question is entirely valid. Yes, there could be privacy concerns. There could be all kinds of other questions you'd ask. My only point in doing this is going through the exercise of showing you two like polar opposites in the spectrum of information structure. Feedback in the sort of strict sense, if I open the textbook and look at sort of what is when people say feedback Nash equilibrium, what do they mean? Well, they're talking about full state feedback, which is to say what I've written here. So my player I's decision at time t depends on the entire state of the game. That's obviously on one, very extreme end of the spectrum of information structure. The other polar opposite being to say, I know where we started, but I know what time it is, but I know nothing else. That's the open loop. So what this question is basically asking is, what happens if I care about something in between? What if I care about information structure where, player one only sees its own states, but not any states pertaining to other players? What happens then? In short, it gets complicated, but I will have something to say about that later in the talk. Looks like maybe another question in the chat.
Yeah, sorry, I was muted. Yeah, there is another question. Since there are some classes of games where apparently open loop and closed loop equilibrium coincide, so how do you comment on that, given that you stated that open loop with receding horizon policy will never result in the feedback equilibrium?
Yeah, that's you're stealing my thunder. Wait till the last section of the talk. I have some things to say about that. Yes, but maybe just to preface it, in zero-sum games, things start to coincide a lot.
Okay, I think we can continue.
Yeah.
Thank you.
Cool. No worries. Thanks for the questions. So let's start to get into actually the technical meat of the talk. What's going on with what is the math behind all these things? So start with the open loop solution in linear quadratic problems. Well, what's an open loop strategy? An open loop strategy in discrete time is just a time index sequence of control actions. So it's just saying, I can look at my watch, say, oh, okay, it's time 3. Here's the action I take. That's what an open loop strategy is. And the way you would solve for that in this context would be to say, okay, well, if my problem, player I's problem, is convex, it's quadratic, but if it's also convex, then the KKT conditions are necessary and sufficient. And if I write down those conditions for all the players and satisfy them, then I'm at an open loop Nash equilibrium. So the first step to sort of do that would be to write down each player's Lagrangian. I've done that here for player I, so I've introduced dual variables, co-states for player I, these lambda I t's. So at every time t is just a Lagrange multiplier for the appropriate dynamics constraint. So this is the Lagrangian, it's the player I's cost minus some inner product of a multiplier and a constraint at every time. Okay. I don't want to dwell on this, but we can write down the rest of the KKT conditions from here. I did it. It's some mild annoyance, but you get some equations. And the thing to realize here is just that this is a linear system of equations. Linear in the states x, the controls u, and the co-states, the multipliers lambda. So if you look at everything going on here, those only enter the right-hand sides linearly. Okay, linear systems are things we know how to solve. So, by the way, probably not a surprise to anyone with a controls background, but this is a very structured linear system of equations, and it's got a Riccati type solution, not the same Riccati equation we would know from a LQR problem, but a very closely related one. And after a bit of algebra, you can find it, and basically this is the solution. Again, I don't want to dwell on it. too much just yet, but we will see these things pop up later in the talk, and here's where they come from. So basically, there's an efficient way to solve that linear system of equations. Okay, so we're going to come back to these just soon, but for now, let's not dwell on the particulars. What changes in the feedback case is that, so we're still looking for a Nash equilibrium, but we're looking for it in the sort of in a larger space of strategies. We're looking now in the space of strategies which are maps from state to action at every time. And actually, we're looking for something a little bit more refined than just a Nash equilibrium in that space of strategies. We're looking for a solution which satisfies a time consistency property, a strong time consistency property, which is to say that, whichever state I happen to be at whatever time I happen to begin, the strategies I find should be in equilibrium from that state and time onward into the future. There's a lot of subtlety to this, and it again, I think, takes quite a bit of time to wrap your head around if you're not used to thinking this way. But just to, in words, describe it, every open loop strategy can easily be written as a feedback strategy. Just, you can say this function gamma should ignore the state, just look at the time and take specify an action that's kind of constant across all states. So it's very easy to write a set of open loop strategies that are in equilibrium, like satisfying the Riccati equations I showed on the last slide, as a feedback equilibrium, or rather an equilibrium in feedback strategies. But that would be a really stupid equilibrium in feedback strategies because it would be ignoring all the state information. So the reason we care about this refinement of strong time consistency that I'm describing is precisely to eliminate those kind of trivial solutions. So in any event, the classical way to kind of derive what these solutions are in the linear quadratic case is through dynamic programming. Again, this won't be a surprise to anyone who's seen LQR before, but the way to do this is to set up an optimal cost to go for each agent, each player I. So here I'm just writing it the standard way. So the cost to go for player I at time t is a function of the state at time t, and it's just sort of what's the minimum cost to go from that point onward. And the subtlety here is that each player now has a version of this problem and a version of this function, and they all need to be in equilibrium with one another, in Nash equilibrium with one another at every state and every time. And the way to do that is, again, just like the standard linear quadratic regulator problem, is to start at the end of time and walk backwards. So what you do is realize, okay, well, at the end of time, big time t, there is no future, so the kind of future cost to go is 0. Assuming that player I's problem is convex, then what you can do is just sort of take the derivative with respect to derivative of the objective with respect to the control input and realize, okay, it's the right thing to do is to do nothing, in the way I've written it down at least. And what we're going to find is that at every time step, the equilibrium cost to go for each player is just going to be some quadratic function of the state, and there will be this matrix ZIT that's going to determine what that function is. If you move back one time step, then the problem looks like this. Now it's not quite so trivial to solve. The way to solve it is to realize, okay, we're still sort of making a convexity assumption for all the players. So if we're doing that, we can write down the first order necessary conditions for the players and massage them a little bit and end up here. So what I've done is just taken each player's first order optimality conditions and summarized them. And what you see is this is for each player I. So it's just a sort of vector equation, linear set of equations for each player. And so there's going to be capital N players. So N copies of this equation where you swap out the superscripts carefully. Now, every player has one of these things, and so this is where things get sort of diverge from the LQR view that we may be used to from a controls perspective. But if you massage that system of equations, you get here. So what I've done is I've basically just factored out all of the equilibrium control decisions for all the players at the penultimate time step, big T minus 1, and written a large system of equations for which that's the unknown. Again, I really wish my mouse was working so I could point this out, but I'm looking at that big stacked vector of the u's. That's the sort of thing we would like to solve for at this time step to figure out what's the equilibrium, Nash equilibrium decisions at this state and at this time. But the point is, it's a linear system of equations, and it depends upon the current state x t minus 1, which is off to the far right in that top equation. Now, we can rearrange things a little bit. And if you factor out the state on the right, it's not too hard to squint at this and realize that actually solving this system of equations, we can sort of solve an equivalent system that gives us the feedback gains that you would expect in a kind of a solution to an LQR problem. There's going to be a linear feedback controller that solves the problem. These matrices P that I've kind of cooked up in the red box, those are those same feedback controllers, linear feedback gains. And here's how you would solve for them. You would basically take the first order optimality conditions for all the players that I wrote down before, massage it to look like a big linear system of equations, and factor out the state and get this. So at the end of the day, in every step of this dynamic program in the feedback Nash equilibrium problem for LQ games, there's a linear system of equations that you need to solve, and it's the one I've highlighted in blue here. Before making any further comments about connections to the open loop system of equations we just saw, I guess the last step to just say and sort of tie it together is that once you solve the system of equations at time t minus 1, we can sort of plug everything back in, figure out in terms of these solution controllers P, what is that matrix Z I said sort of determines the quadratic cost to go for each player at the penultimate time step. So you'd sort of just substitute back into the objective and obtain this recurrence that I've written down here. We're sort of, I'm giving you more details than we really need right now, but just a few things to point out. This is not giving us the same solution we had in the open loop case. There's tons of differences, but maybe the most obvious one to point out is relates back to some of these terms I mentioned were encoding politeness, if you like. So here, just in that recurrence for cost to go, this term I'm highlighting in the blue box, these are basically matrices that were showing up in player I's objective that were determining the contribution to player I's cost of player J's actions at time t minus 1. And so those were kind of encoding, how much, the player 1 may, not want to take actions which make player 2, have to take wild evasive action or something like this. So back when I showed you the system of equations and the Riccati solutions for the open loop case, it turned out actually, if we're being super careful to check, these terms were not even present in the solution. And there are tons of other differences too. So just to maybe explain what, where did they go in the open loop solution? So if you think about politeness as caring about others' effort, in the abstract, I can sort of think about a polite, an objective that's encoding this sort of politeness for player 1 as some sort of otherwise nominal objective that depends upon the state and only player 1's decisions, U1, plus, some, let's say, norm of player 2's actions over time. Well, the way we derived the open loop solution was by looking at the KKT conditions. So basically taking derivatives of Lagrangians with respect to decision variables. And if you do that, basically you end up taking the derivative of the norm of U2 with respect to U1 and the state X. And that's just going to immediately disappear. So in open loop, that's where this term went. It disappeared as soon as we took a derivative. But in feedback, what happens is that actually the process of the dynamic program encodes that the sort of future state at time t+1 depends upon the action all the players take at time t, and so and sort of moving forward, the actions player take at time t+1 depends upon the state at t+1. So player 1 can indirectly influence the action of player 2 at the next time step by taking an action which moves the state in a particular way. And that subtle connection is exactly what the dynamic program captures. So the TLDR is that that term I've crossed out doesn't disappear in feedback. Okay. So hopefully that gives a sort of quick and dirty introduction to the sort of polar opposite information structures of open loop and feedback and how you would solve for them in these classic linear quadratic problems. What I want to do now for the remainder of the talk is walk through 3 kind of quick vignettes of how we've used this in my group in recent projects. So all these will be pretty quick. And the first one is sort of just trying to ask this question of how can we approximate feedback Nash equilibrium strategies in a way that is sort of conscious of communication or sort of sensing limitations. So I actually got exposed to this problem through talking with a friend at NASA JPL, and he was on this project called Cadre, which if you've not heard of it, it's a tech demo that they're basically sending 3 rovers to the moon. They're pretty small. Actually, interestingly, they're the first sort of deployment of non-radiation hardened compute to space. It's just a tech demo, but that's the idea. So they're sending up, I think, some sort of Jetson boards on these rovers. And the idea is that the rovers have to maintain pretty accurate formation because they have some sort of ground penetrating radar that they're going to be trying to image the subsurface structure of a particular part of the moon. So they have to be maintaining accurate formation in order for those measurements to be interpretable. Now, the catch is that in order to maintain that formation, the sort of typical thing you would want to do is to have each agent sort of communicate its estimate of its position to the others or directly sense where are the others. And all of that sensing and communication costs energy that is very precious to these rovers. So if you can sort of come up with a strategy that each of the agents can deploy, which minimizes the need for communication and sensing, it would be beneficial. So turns out actually there's a very clean way to connect this problem to things we just saw. So think about the linear system of equations that you have to solve in order to find the feedback Nash equilibrium strategies at every time step. It's this one I've shown here. There's some atrocious looking matrix S that multiplies all of the linear feedback gains, P's, and there's a right-hand side. Well, inter-agent sort of dependence, sensing, communication, however you look at it, this can be understood as kind of related to a blocked structure of these matrices P. So what's happening is that if player I's equilibrium decision at time t, u I star t, is minus pit times xt, then basically this vector x is just stacking up all of the states corresponding to each agent. And so the kind of blocks of columns of this matrix P are hitting each of those groups of state variables. And so the blue block that I've highlighted is multiplying, player 2's state variables. So then, this is, if this blue matrix were to be 0, this would be like saying, oh, player I does not care about player 2 at time t. So player I can like ignore, can not sense where is player 2 and still make the same decision. So at the end of the day, in order to reduce these sort of inter-agent dependencies, the way you can do it is by trying to zero out entire blocks of these feedback control gains. And this sort of naturally leads us to like a lasso type formulation. It's a sort of slight variant of lasso, but basically you can turn that linear system of equations into a conic program to solve that looks like this. So what I've done is I've taken the kind of L2 residual from the original linear system of equations we wanted to solve. That's the first term in this objective. And the second term is just sort of adding up for all the players some scaled Frobenius norm of all of the blocks in their feedback controls. So this is basically these Frobenius norms are gonna essentially have the effect of driving entire blocks to 0 at a time. And this, we didn't invent this. This is a very common variant of lasso called group lasso, but it's sort of elegant that can be applied this way. And what's also very neat about this is that this is happening at every step in a dynamic program. So what that means is that you're basically when you look at this problem at some intermediate time, it's automatically able to account for the sort of impact that sparsity now has, or density now has, on future sparsity. So what I mean is, we can all sort of show this example of like a 4-player navigation problem. And I'm going to kind of show these color-coded things that are sort of showing what happens when we regularize and when we don't on the left and on the right. And what you're going to see is that over time, of course, the regularized solution ends up being much sparser than the nominal unregularized solution. But actually, there's sort of interesting patterns that are time dependent. So in order to see it, I'll just play a quick video, and I'll play it maybe twice just so we can sort of see what's happening. Right, so before I play it again, just the one high-level pattern is that when everybody's far away from each other, either early on or very late in the trajectory, everything's pretty sparse. Basically, every player only cares about their own states, the block diagonal. But then when they get close to each other, on the right-hand side, the sort of nominal feedback Nash solution is one that's pretty much fully dense, but the sparse one is going to have particular sparsity patterns that start to arise. Okay, let me play this one more time. Right, so if I pause, oh shoot, if I cannot, oh no, I see my mouse, very nice. So if I pause right here, you can sort of see that there's, for example, like player 4 caring about player 1 in the sort of nominal feedback Nash equilibrium, but once you regularize, they don't care at all. And I forget which is which here, unfortunately, but.
Excuse me, David, just as a clarification, is this selecting a sparse Nash equilibrium solution, or is it approximating a Nash equilibrium solution by a sparse one?
It's approximating a Nash equilibrium with a sparse one. Yes.
Okay, thank you.
So, just to kind of quick highlight that, I guess, phenomenon I'm trying to mention in the video, what I did is I just went ahead and plotted for each of the players. So each player gets one of these 4 plots. At different levels of regularization, how many other players do they care about over time? That's what these figures are showing, and each level of regularization is a different color. As we kind of crank up the regularization, of course, we expect sparser solutions. But what's interesting is actually that, it's not like at a particular time, if I crank up regularization, I always get a sparser solution. So for example, if you look at the bottom left figure, let me get my mouse back. Oh, I don't have my mouse anyway. So look at the bottom left figure. When you go from lambda 0, no regularization, total, this is exactly a feedback Nash solution. At time step around like 60 something, player 3 is caring only about 3 other players. In other words, they care about themselves and 2 others. They don't care about one of them. But when I crank up regularization to 20, lambda 20, the red curve, actually there's this spike, and in the sparse solution, we care about, player 3 cares about all the players, all 4 of them. And the reason this happens is because player 3 realizes, okay, well, if I quick sense this 4th player now, then that'll allow me to like not look at any players later, right? So basically you see the red curve like suddenly drop to 1, and basically I'm only looking at myself. Player 3 is only looking at themselves, sort of around time step like 85 or so. And so that's So that's exactly happening because of this dynamic programming structure, where basically, because we're working out what the sparsity should be at the end of time before the penultimate time and so on, when we solve at some intermediate time, it's accounting for future sparsity. And so it sort of is realizing, okay, well, I can take an action now that is requiring me to sense more an additional other agents, because it will allow me to be sparse later. So anyway, those sorts of patterns start to arise.
There is a question here.
Shoot.
That's really interesting. My question is, can this be interpreted or encoded differently as a stage cost to communication? Would you be able
Yes,
to
so
indicate something like this if we add a stage cost to communication?
yes. So that can be done, and actually people do that, though not. I haven't seen anybody explicitly do that in the context of LQ games. I've seen people do that in the context of actually, there may be one paper that does that I'm forgetting. But the upshot is, if you do that, then it breaks the convex structure of the dynamic program. It almost certainly will. So because then what you're doing is your decision variable ends up being like the feedback gain itself, the sort of P matrices I'm calling P. And so as soon as you introduce a cost directly on P, it sort of like if player one cares about some norm of blocks of P, you're basically changing the structure of the DP a lot, and it's going to end up, as far as we could tell, breaking all the convexity, which makes it obviously quite painful. Yeah, I have more to say on that, but maybe let me defer till after if that's okay.
Okay.
Okay, so for the sake of time, I don't want to dwell on the theoretical results we had on this, but just to quickly mention them. Sort of the main theoretical results we were able to show for this this sort of group lasso sparsity inducing DP is that so for a game in which the feedback Riccati recursion kind of converges as you take the time horizon large, and you get sort of a time invariant solution. In those types of settings, we're able to construct kind of bounds on the approximation error between like the sparse feedback Nash equilibrium and the correct one. And the technique is a bit involved, but that's the type of result we're able to prove. So we're able to sort of bound the approximation error as a function of lambda. Okay, so let me kind of quick walk through two other vignettes. They'll be a bit quicker just for the sake of time, but happy to answer more questions offline afterward. So the next sort of story I want to tell you about is what happens when the information structure changes during an interaction. So if we know that let's say the information structure will change from feedback to open loop at a particular time step, or in some sort of subset of the states we have feedback access, but in some other subset of the state space we don't. What happens? Turns out actually this is a super practical problem. So every time you're overtaking a big truck on the highway and you can't see the oncoming traffic, what you do is you sort of understand that if you sort of pop out behind the big truck, you'll see the oncoming traffic, you'll have feedback information structure, and you will probably want to solve a feedback Nash problem. But before you do that, you don't see the oncoming traffic, and essentially you need to make an open loop strategy. So basically, these types of interactions directly, necessitate solutions to these problems. It turns out that in linear quadratic problems, this is actually quite easy to do, at least with one or two minor caveats. So the way to see where this comes from is that, and I'll copy them in a second, but basically the Riccati solution to the open loop problem and the also Riccati type solutions to the feedback problem encode cost to go as quadratic functions of state, and that quadratic function is either sort of valid at any state in the feedback case, or valid just along locally along the equilibrium trajectory in the open loop case. But in any event, in the open loop case, we had sort of a Riccati solution that looked like this. In the feedback case, the solution we had sort of roughly looked like this. And the matrix M in the open loop case plays essentially the same role as the matrix Z in the feedback case. So both of these things, if you look on the top right, they're kind of encoding, they're accumulating state-related costs, and I guess control-related costs as well. So they're playing essentially the exact same role. And from there, it's a lot of algebra, but one can show that you can derive. So if you know that there are going to be periods of open loop or occlusion and periods of visibility or feedback, what you can do is sort of solve a dynamic program and work your way backwards in every kind of open loop period, solve the open loop KKT system, solve the open loop Riccati recursion. And then as soon as you transition to the sort of period of visibility, the feedback period, just take the cost to go for each player, that matrix Z, and plug it in as a terminal cost as sort of the M matrix for the open loop problem. Sorry, for the maybe I've got it flipped. You're taking the cost to go for the open loop problem, the M matrix, plugging it as the terminal cost Q for the feedback one in blue here, and work your way backwards. And so you sort of chain these Riccati recursions together. And sort of the connection as you walk backward in time is always by plugging in the cost to go at the initial state of one time interval as the terminal cost for the previous interval. And like I said, it's a lot of algebra to show that this is correct, but actually we can show that this does recover the proper solution to the problem. And it again only involves solving linear systems of equations. The last thing I want to tell you about gets to the earlier question of sort of, are there circumstances in which open loop and feedback solutions actually are not so different? Before saying that, I want to also say that, everything I basically told you about, I characterize everything as purely related to linear quadratic problems, but actually the reason I'm telling you all this is because linear quadratic problems are the kind of fundamental building block for solving any more general problem. And we've got several papers that kind of expose these ideas and connections to Newton type algorithms and sequential quadratic programming and so on. But basically, everything we can do for linear quadratic problems, we can naturally extend to derive sort of local solutions for non-convex nonlinear problems. So in that setting, the reason I mentioned this is just because when you're beyond the linear quadratic setting, it turns out that open loop Nash solutions are way, way easier to compute than feedback Nash equilibrium solutions. They're way less involved. And actually, in the feedback setting, we can really not even compute these things exactly. We can only compute approximations. And even less satisfying, the approximations we can compute are we don't yet have good bounds on the approximation error. We can bound some components of error, but not others, and only in some contexts. So the upshot of all this being is that if you could find a setting where you know that the open loop solution recovers the feedback solution, then it would be way, way easier to solve for the open loop solution. And you should totally do that. So I guess the quick story to tell is that, well, actually, let me tell the story in a second. So yeah, so like I said, so in general, we know that I already showed you this kind of counterexample where the feedback and the open loop solutions, were wildly different, even a linear quadratic problem. So, in general, knowing nothing else, if you actually do have access to feedback information, probably you should find a feedback solution. But in zero-sum games, it turns out that the story is more subtle. And the story that actually the way I kind of came to care about this is because I was working on a project with a contact who is sort of trying to frame satellite rendezvous problems as differential games. And And of course, he was interested in zero-sum problems because he's modeling kind of adversarial interactions in space, whatever. And the upshot is that we worked on an open loop solver for the specific type of problem that was arising in that application, with the intention of then using what we had learned in building the open loop algorithm to build one to find the feedback Nash solution. And then at some point, a year into the project, a third person sends me a screenshot from a textbook that basically says, oh, actually, in some types of zero-sum games, these are the same. These solution concepts coincide. And so I was totally shocked and embarrassed that I hadn't known this. But it turns out, actually, there are a lot of classical results that say this, and none of them exactly covered the case we needed to care about. So we did some work on it as well, and I wanted to just share that with you. So the classical result is just that for convex concave zero-sum linear quadratic problems, basically when you have unique open loop solutions, they also kind of recover feedback solutions or vice versa. Essentially, yeah, like I said, the details is that if solutions are unique, they kind of coincide between open loop and feedback solutions. They recover the same state trajectories. There's also classical results beyond the linear quadratic case, which is the case we were caring about arbitrary nonlinear dynamics that described space maneuvers. But if you have a strongly unique feedback and open loop solutions, then they start to coincide. And so this concept of strong uniqueness is it's kind of a refinement of uniqueness, but it's saying that not only is there a unique Nash equilibrium, but actually the best response map for each player is a singleton. So it's saying that for when I fix all the other players' strategies, I have a unique best response. So it's a very, very strict condition. Rock, paper, scissors doesn't satisfy that condition. So these results are nice, but they have a very, very strict requirement that it's impossible to validate, to verify in practice for any serious application problem you'd have. So we were interested in basically generalizing what can we say about these relationships between open loop and feedback Nash solutions, but when all we know is local structure, all we know is sort of local derivative information. So I realized we're kind of probably getting over time at this point. So the upshot of this is we were able to prove that essentially when all you care about is local equilibrium structure, sort of to first and second order, each player is at a local minimizer for their problem, or in a zero-sum game, it's a local saddle point. We're able to show that actually these open loop and feedback solutions also coincide. So that's what these are saying. Rather than dwell on this, maybe it's better to take any direct questions about it in a minute. So let me just say that the take-home messages I want to leave you with are that games are super flexible models of interaction, particularly with regard to information structure. And at least in my mind, information structure is like the most interesting and underexplored part of game theory. And the last thing is, even though these things have been studied for decades, there are still pretty fundamental, exciting results out there. Thanks so much for your attention and for coming today. I'd love to take questions, and I'd love to thank all of my students and my postdoc, in particular, the folks I've highlighted. This is their work, so thanks to them.
Thank you. Thank you. That was a fantastic talk. Are there any questions from the audience? Actually, there is one from
Go first, Tony.
yeah, there is one from the chat. Are there ways to quantify the information structure?
Are there ways to quantify the information structure? I think, I guess that's a bit of a loaded, complicated question. I think you'll certainly see people. So for example, there was an earlier question about like privacy. So if maybe I've seen people do things like quantify, like how much noise is there in a, let's say, differentially private mechanism for hiding player one's state from player two. So that would be like one mechanism for quantifying information structure. But I think in the strict sense, like strict textbook sense of information structure. The way it's always described is as sort of a pattern of subsets of states which are indistinguishable to certain players. And so there's not really a direct classical way to quantify those structures, although I guess natural things would be to sort of maybe look at cardinality of sets in discrete cases and things like this. Yeah, I don't have a great answer for you on that.
Thank you. Do you have time for another question? We understand.
Yes.
So I had one question about feedback, like in linear system, like to find the feedback equilibria. So you need to kind of solve this Riccati, I guess, equation to find the matrix P, right?
Yes.
So how much more difficult is it to find this matrix, for example, compared to like a classical MPC problem in which you need to find you need to solve the Riccati equation to find the P matrix for the infinite horizon LQR. How complicated is this for a setting, like a game theory setting in closed loop? Is it the main bottleneck? Because when I read first about this, is that when you have many agents, it becomes not that easy to find this matrix kind of.
So sorry, I'm trying to find the easiest slide to see this on, but I think this one kind of exposes it. So basically the complexity of solving this problem, you can just sort of stare at the size of these of this linear system of equations, and it's gonna the number of rows will be let's see, the number of rows will be the number of total control inputs for all players.
Yeah.
And the number of columns will be should be the number of state variables for the game. So basically that if each player has one control input and each player has one state, then this is basically like n by n.
Yeah.
Players. Solving, it's a dense linear system in general, so it'll take cubic complexity to solve. So
okay. Yeah. So you cannot exploit sparsity directly, like in finding the solution to this, let's say.
Oh yeah. So just strictly so before finding any sort of sparse policies or whatever, the sort of complexity of the standard Riccati recursion would be cubic in the number of players.
Okay.
And then and linear in the number of time steps. As soon as you are doing this thing I'm describing on this particular slide about sort of trying to find sparse solutions, oops, it went too far. But anyway, you're just solving you're solving a slightly harder problem at every time step. It's instead of just solving a square linear system, the actual problem is this one. So this is just a SOCP. So it's a more complicated problem, but it's still not that hard.
Okay. Thanks.
I think that's about the time that we had. Again, I want to thank you again, Professor Fridovich-Keil, sorry. And thank you so much for contributing to the seminar series. We'll meet again next week with Dr. Nordmann from EMPA Zurich. And yeah, you're all warmly invited to join also for the seminar of next week. For now, thank you again, and have a great rest of the day.
Thanks.
Thank you so much.